Hello, everyone. Thank you for tuning in to the virtual dairy nutrition management series. I'd like to thank the conference organizers for providing me this opportunity to share my thoughts on why dairy emissions models are an important component of the industry's path to net zero emissions. So I want to start by saying that one of the reasons that addressing things like climate change and net zero emissions is so challenging is the enormity of the problem. And even if we take a small subset of the global climate change problem, like achieving net zero emissions for dairy farms, it's still a huge task and can seem insurmountable for an individual to act on. And then another big part of that challenge is that the goals and outcomes are really intangible. I mean, when was the last time you saw or held a greenhouse gas? And day to day, how do you know if you're lowering or increasing your emissions? It's really difficult to connect the actions that you do today to the distant consequences of climate change. And so, unlike decisions that change your milk production, which are tangible outcomes that you can track and see the progress in relation and response to your actions, how we influence our greenhouse gas emissions is really a difficult problem. And so even though the basic concepts of greenhouse gases and how they influence global temperatures and how global temperatures might influence climate are pretty straightforward, and we can easily put definite numbers to connect things like a gallon of gasoline to the amount of CO2 produced when it's burned, it's still really difficult to imagine how we can quantify the carbon footprint of something like a whole farm. And so if anyone out there that's listening has actually measured the greenhouse gas emissions from a farm, please get in touch with me because I can retire and go live on a beach somewhere. I mean, it would be great if we could just put a dome over our farms, measure the gas exchange of the entire farm operation under different management and weather conditions. We could check our CO2, methane, and nitrous oxide meters regularly to know how we're doing. But we all know, or some of us may remember, that that didn't work out too well for Springfield in the Simpsons movie. And otherwise, it's just obviously pretty impractical. So this is where models come in. Models ground this really abstract and complex challenge of quantifying the gas produced from a whole farm or even the entire production chain in the reality of concrete numbers. And they do this by breaking the larger question down into pieces. The most basic description of a dairy farm emissions model is the sum of smaller equations that describe the pieces of the farm that has been broken down into smaller components. The work of building a dairy emissions model is deciding how small each of these pieces should be, and then finding and developing the mathematical equations that describe the emissions from each of these components. And there are many, many ways to accomplish this. And so I like to compare building a model to building a house or remodeling a house, in that you have a million different decisions to make at every step of the process. And so I'm going to describe some of these larger structural decisions that have to be made up front, because I think that they're important factors in understanding how the model can be used. One of the first decisions that needs to be made is how will the model represent time, whether it will be static or dynamic. Will it represent a single snapshot in time, be a static model, or will it be dynamic and provide estimates of outcomes and changes over a longer course of time, at regular time intervals? And in either of these options, the model could represent different lengths of time. It could represent a single second, minute, hour, or day, or it could go for months, years, or decades. The next important decision is to define the boundaries of the system you're representing. And unlike other scientific fields that use models, for like engineering, for example, agricultural systems don't have well-defined borders. If your system is a field, for example, how deep do you need to represent the soil profile in order to get an adequate assessment of leaching and runoff and emissions? How much of the field's management and nutrient history needs to be represented? If the boundary is a farm, do you account for emissions from imported feed, animals, and equipment? How far into an imported product's history do you need to dig in order to attribute the correct amount of that footprint to the farm? Similarly, if your system is the whole food chain, where does that food chain begin and end? Does it start at the field and end at the fridge? Does it need to go all the way to the fork and include waste after the consumer buys it? How do you deal with the allocation of impact of the use of various waste products that enter and leave your system? All really important questions that have to be decided as you're building the model. I refer to the next decision as the modeling ethos. So in selecting and developing the equations that provide the foundation of the model, the developer has to choose between two general modeling principles, whether the model is empirical or mechanistic. Empirical models are equations derived from statistical relationships that are not constricted by the underlying mechanisms, or at least our understanding of what those underlying mechanisms are. However, in a mechanistic model, the researcher defines the structure of the equations based on what we know about the behavior of that process. These two types of models are often referred to as black box and white box models. Black box for empirical because we ignore the underlying processes, and white box because we provide a window into the behavior of the system through our mathematical equations. But more and more people are relying on both of these strategies in what has been coined a gray box modeling. And so the final structural decision I want to highlight is that the modeler has to decide how these individual components of the model will be put together to recreate the whole system of interest. Specifically, they have to decide if the subsystems, so the animal, the herd, the crop in the field, how they will be represented as a whole. And so will they be independent of each other, or will they build dependency into the model to represent the interconnected responses of the system? Oftentimes in agricultural systems, and definitely in dairy farms, the response of one part of the system, for example, the yield of a silage field and the quality of that silage, will influence the outcome in another part of the system, for example, milk production in the milking parlor. And so, as I mentioned, I'm highlighting these decisions in particular because the answer to each question is driven by the intended application. And dairy emissions models all have different structures, and those structures inform the applications, and how those models are applied will define how they can support the dairy industry on our path to achieving net zero emissions. And so I just love this image, but as in biology, form follows function. And obviously, this cow has evolved exceptionally well over millions of years in order to become the perfect couch for this dog. And the three main model applications that any model developer is often working towards is to create an inventory of dairy emissions, to use the model as a decision support tool, or for pure research application to develop new knowledge about how the system functions. And there's a lot of overlap between the research models and the other two applications, because often a model will start out as a research tool and grow into use as one of the other two applications. And so while many models will fit into these two overlapping areas of research and decision support, or research and inventory, there's not a lot of overlap in this area in between decision support and inventory models. And so that's why I've created this Venn diagram with a really small area in between, because there are a few, if any, models that fit into that category. And then finally, the models that are applied as inventory models or decision support models are really the ones that are going to impact our path to net zero emissions. So I'm going to focus on those two types of models. And so I've spent a lot of time telling you about models and how they're built and what goes into them, but you're probably thinking, how do these models actually help us to reduce dairy's carbon footprint? We can put numbers on the impact, but that doesn't actually change the outcome. Things that will actually change the outcome are feeding supplements that will reduce enteric methane, building, designing, and installing anaerobic digesters will change our carbon footprint. And you would be totally correct. Models alone and just running them won't change our carbon footprint. If we designed, built, and ran the models, looked at the numbers, and then moved on with our day with business as usual, models wouldn't help us at all. Another way you might use models, and that a way that they're actually used in practice, is that you can use them to compare our footprint with other foods and industries. And this is the outcome of this is often just to point fingers and argue about who is responsible for climate change. And that still doesn't get us anywhere. And so I hope anyone out there that is watching agrees that a better choice would be to actually use these models as a guide to define and direct our path to actually achieve the goal that we've set for us, which is to get to net zero emissions for the dairy industry by 2050. So I love this quote by Lewis Carroll, and it's actually a paraphrase from a conversation between Alice and the Cheshire Cat. But I think it exactly describes the first reason that we need dairy emissions models in order to reach our emissions goals. If you don't know where you're going, any road will get you there. And so there's no way that we can transition the dairy industry of today into an efficient and sustainable and carbon neutral one if we don't know how far we have to go to get there. And this is where inventories come in. Inventories give us the big picture. They set our baseline or our starting point, where we are now, and then they tell us how far we need to go to get to our target. An example of an inventory model that many of you may be familiar with is an assessment by Capper, Cady, and Bauman. And so in that study, they estimated the national greenhouse gas emissions in 1994, or 1944, excuse me, and 2007. And they came up with an estimate in 2007 of 1.35 kilograms of carbon dioxide equivalent emissions per kilogram of milk. That same group in a follow-up study re-estimated the 2007 footprint in addition to the footprint in 2017. And you'll notice that in the new model that they developed, they came up with a new estimate for the footprint of the 2007 emissions. And this is a result of a few different factors that combined together, but including that they changed their model structure. But one of the factors was that there was an additional availability of data that they used in their 2020 estimate of the 2007 and 2017 inventories. And so the availability of data is a really important topic that influences model outcomes, and one that I'll come back to later. A few other inventory type models that you've probably heard of and may be familiar with is the life cycle assessment model, an estimate done by Greg Toma and colleagues that was published in 2013, and a more recent regional evaluation that was conducted by a team of ARS scientists led by Al Rotz. And then this not yet published model, the Foods Cubes model, done by a University of Minnesota led team. And so I highlight these examples to emphasize a few different points. So the first is that they all have different methods. And so because they all have different methods, they will all have different estimates. different numbers that are produced. And you're probably thinking, we're using these models to give us concrete numbers, but these numbers aren't concrete. And I think that we need to be okay with that variation and uncertainty. And we have to expect these differences and learn to interpret the outcomes within the context of the methods and the data used. The other point of highlighting these different inventory methods is that they can be at different scales. And so that's part of interpreting the different outcomes, the different estimates within the methods that they're used. And so in particular, the regional assessment by Al Rotz and his team is done at a regional grouping of states rather than a national level. And so you would expect that the different regions of the US would have a different footprint than the overall average of the United States. And then finally, that they will often have different boundaries. And this is most easily highlighted by the LCA done by Greg Thoma and his colleagues, in that they included the entire production chain. And so while the regional assessment and the study by Capper and Katie stopped at the farm level, the LCA that Thoma and colleagues published included the processing and retail footprints in addition to the farm level emissions. And so to summarize inventory models, the primary utility of these types of models is to establish a baseline, to track progress and set goals. Some key features of these models that distinguish them from decision support models is that they are static, they don't change over time, and maybe more importantly, that they're often retrospective. And so they are snapshots of a historical period. And finally, that they usually are reserved for longer periods, with the minimum time being a single year. And so how do decision support tools differ from inventories and how they help us to get to net zero? If inventories tell us where we are and where we want to go, then decision support tools tell us how to get from point A to point B. They map out the path. Without decision support tools, we don't actually know how to get to where we're going. We may have a general idea of the direction and be able to take some steps that point us in the right vicinity and feel good about what we're doing. But we definitely won't be on the most direct route, and we possibly might not even get there in the end. And so this is why we need decision support tools to really map out the path to achieving net zero emissions and enable us to frequently check our progress along the way. Many people in the dairy industry work with some form of decision support tool already on a regular basis. And these decision support tools are models that help formulate rations, ones that track feed delivery and consumption, ones that make recommendations about field management and forage quality. The list is almost endless in terms of the number of models and decision support tools available for dairy farmers. And the example I show here, I just want to mention are just ones that I've used in the past that I'm pulling out to provide concrete examples. And I'm not recommending any of these models in particular or saying that they're better or worse than the others that are available. However, I will say that all of these tools and others not mentioned here take in data about the farm, process it, run that data through equations and models of varying complexity, and return information that supports some kind of decision that has to be made in order to keep the farm running. And so the way that dairy emissions models can inform the path to net zero is similar in that they will take in data from the farm, process and analyze it, and provide some kind of information that can be acted on in terms of how the management is influencing the carbon emissions. I will say that emissions models are a bit different than ration formulation or feed tracker software in that emissions models won't likely need to be used every day, but rather at a slightly longer intervals or time periods. But they can still iteratively set the course and adjust the management trajectory as needed throughout the year or throughout the course of several years. However, I'll just put a caveat to that statement in that there are many dairy emissions models that are currently in use as decision support tools that function at the time step of a year or only provide estimates at on an annual basis. And there is definitely value in that in the use of decision support tools at that time step as well. But as we begin to integrate information and feedback about farm emissions with and the response to management decision process, I feel strongly that we need to start using these dairy emissions models at a smaller time step than a year. And so these are just a few of the decision support tools, dairy emissions models that are used as decision support tools commonly in the US that I want to highlight. So there's Comet Farm, Cool Farm Tool, Farm ES or the Farm Environmental Stewardship Model, the DNDC, and the Integrated Farm Systems Model or IFSM. So to summarize, decision support tools differ from inventory models in that they can predict future outcomes instead of focusing on retrospective analysis and provide feedback and information that influences management decisions. Some key features of decision support models are that they can be either static or dynamic and are best used if they can update emissions estimates more frequently than inventory models do. Another distinction between the two types of models that you may have noticed is the physical scale. And so the inventory models are often reserved for larger spatial scales like the region, country, or globe, while decision support tools operate at smaller scales like the field, cow, or farm. And so I'm going to focus on the farm scale models in this talk because I believe that is a really important level of decision making that is one, difficult to interpret and integrate all the important information to make the best decision without a model, and two, one that isn't well supported by a plethora of decision support tools. And so I've put the models that I've mentioned so far into that Venn diagram that I showed earlier. This list of models is by no means comprehensive in terms of the available dairy emissions models out there, but I wanted to just put these in there as to give you an idea of how I think each of these models that I've mentioned or will be mentioning fits into this Venn diagram. And so Comet Farm, Cool Farm Tool, Farm ES, and CLEM, which is an Australian model, are all very solidly in the decision support tool developed specifically for that purpose. Whereas the Integrated Farm Systems model and Manure DDNC were developed primarily as research models, but have evolved into application as decision support tools. Similarly, the inventory models that I mentioned, most of them were initiated as research studies. However, they provide useful information to inventory the dairy industry as a whole, and can have useful applications for that purpose. And so now I want to give a little bit of information about about some specific models that I think will help to give you an idea about the important features that are needed to focus on and understand when choosing which model you might use for a decision support tool. And so I'm starting with Comet Farms. So some key model features is that Comet Farm only focuses on greenhouse gas emissions, so it doesn't provide any other environmental impacts, which is fine for focusing on the path to net zero. And this model was built on as a decision support tool that is connected to the DECENT research model. And so because of that, it has features long-term simulation of carbon cycling and greenhouse gas emissions that is very detailed and one of the more robust representation of carbon cycling in these types of models. It's also capable of representing multiple livestock species, which can be a nice feature if you are interested in representing beef and swine and other livestock. However, I will say that it does focus on the field emissions. That's where its strengths lie. And it has limited options for altering the predictions of emissions from a variety of different animal management practices. However, it is quite user-friendly. And another strength is that it has an automated method to import soil data into the model input simulation. The next model is the Cool Farm tool. This is a relatively new model on the scene and comes out of Europe as a proprietary model. So it's not as easy to know or understand what the underlying equations that are driving the emissions estimates are. However, it is nice because it includes some key ecosystem service metrics in addition to greenhouse gas emissions, like water use and biodiversity impacts. Also, the nice feature of it being a proprietary model is that it has a really nice user interface and is very easy to use. However, it is somewhat limited in its ability to represent US dairy farm practices, in particular, any animal husbandry and management that might influence greenhouse gas emissions. Manure DDNC, or the denitrification and decomposition model, is another model that started as a research model. And so this model that started as just, or I guess I should say the Manure DDNC grew out of the DDNC model to represent animals. And so the real strength of this model is that it has very detailed process models of soil decomposition and denitrification, right, in its name. And this model operates on daily time step and is continuous simulation that can be conducted throughout many years. And so its strength is really in those soil nutrient cycling or the soil biogeochemical processes. But this means that this focus means that they haven't yet included any representation of machinery or the structure or how resource use might impact emissions. And that the representation of crops and animals has a lot less detail and relies on a lot of user estimated inputs, which means that it's not as responsive to differences in animal management practices. The Integrated Farm Systems Model, IFSM, is the model that has been built by Al Rotz, that ARS team that I mentioned earlier, that published the regional estimate that in the inventory. And so this is one of the few models I'd say that kind of spans all three applications, from research to decision support to inventory. But really its home and its comfort zone is as a research model. I will say that some of the strengths of this model is that it does simulate the major components of US dairy farms. And by that, I mean the primary management practices. It also has very comprehensive environmental impacts and outcomes, similar to Cool Farm Tool, but even more so. It simulates water quality impacts, water use, air emissions, air quality emissions, as well as greenhouse gas emissions. It also includes options for simulating grazing and beef systems, which not all models do. This model deals with time in a slightly different way than a lot of models, in that it has a daily time step and simulates continuously for a year, and then does that for 25 years and averages those 25 years of simulation. Another strength of this model is it has a really good representation of farm machinery and barn structure and how those components of the farm contribute to energy use and emissions. So switching gears a little bit, now that you have a greater understanding of what goes into model development and some of the different models that are out there, I'll say that in spite of all of their differences in what they predict and how they predict it and what the predictions can be used for, a common feature of all dairy emissions models is that they rely on the same thing. And this is high quality, regularly available data. One of the greatest challenges of putting together an accurate inventory at any spatial scale, whether it's from a single farm to the globe, is collecting and compiling and integrating all of the disparate types of data, types and forms that are needed. And so this is really a bottleneck, I would say, in how we are using models to inform our decisions at any level, whether that's just setting benchmarking and goals or making decisions at an individual farm level, is how we can collect and integrate and use this data to inform our dairy emissions estimates. And so as everyone watching out there knows, is that every day a typical dairy collects huge amounts of data that are used in a variety of ways, whether it's through those other types of decision support models that I've mentioned, or it is informing a nutrient management plan, or just informing the paycheck that they get from whoever is buying the milk. So my question is, how can we harness that data to inform our dairy emissions support tools so that they can provide us better and more accurate inventories? They can help us make better predictions and assessments of how new management practices will influence emissions and production outcomes. And also, how can regularly collected data help us do each of these inventory and decision support actions at regular intervals? And so, as you can imagine, because it's not done already, collecting, processing, and integrating commercial farm data and building emissions models that can integrate and use this data efficiently are really not easy tasks. Otherwise, obviously, they would have been done already. But we are working on it, and I think that it is a worthwhile goal to aspire to. And so I'm working with a team, a larger team that includes people from Cornell, UW-Madison, University of Arkansas, UC Davis, and many ARS scientists to build a new dairy farm systems model, the ruminant farm systems model, or RUFUS. And so the RUFUS model we are describing as a next generation model. And this model will estimate greenhouse gas emissions in addition to some of those other important environmental outcomes mentioned, like water quality impacts, carbon sequestration, energy use, water use, resource use. And at its initial outset, this model, like many others, will be a research tool, but our goal is to transition it into a decision support tool quickly and to build it to be interoperable with models at larger scales, with the hope that it can inform inventory models in the future as well. And thus, this will cut out the disconnect between decision support tools and inventory models, and hopefully fill in that space in the Venn diagram where there's so few models that are achieving both goals. And then in addition, and probably more importantly than being interoperable with other models, we are building RUFUS to integrate with commercial farm data and working towards this in collaboration, relying really on our partners at UW-Madison. And so RUFUS collaborator Victor Cabrera is leading a team at UW-Madison to build a platform coined Dairy Brain. And so Dairy Brain in itself is actually a decision support tool as well. And this tool or platform can integrate disparate sources of data from the dairy farm and provide insights about how the farm is performing on a daily basis. And so we are connecting the Dairy Brain data management platform to the Rufus model as a way to efficiently import real farm data into the Rufus model on a regular basis. And so connecting this daily data management and decision support platform with a model that predicts environmental outcomes can really increase the utility of a dairy emissions model or an environmental impact model as a decision support tool. And so when these platforms are built and connected, the goal is to be able to update estimates of farm level dairy emissions on a regular basis, to simulate the impacts of new technologies and management practices in the future in order to identify the best suite of mitigation options for each farm, and to use the real farm data to improve and update the Rufus model algorithms as needed. Unfortunately, these are still works in progress and they're not done. But until they're ready to be applied in the real world, we can still work with the models and tools that we have available to us. And so just to wrap things up, if we're going to achieve our goals of building an industry that does not contribute to climate change or has net zero emissions, we will need to strategically use dairy emission models to get us there. So we'll need to use inventory models to assess the current state of the industry and set goals and benchmark to the future. Where are we now? Where do we need to go to get to our final goal? And what are some intermediate goals in order to get us there? We'll also need to plan our path to get there with decision support tools and use them to assess progress in between these larger scale benchmarks set by the inventory models along the way. And then finally, once we have the path laid out for us by decision support tools, we need to increase and improve our data collection methods in order to inform both of these types of models so that our estimates, both at the inventory and decision support level, are the most accurate reflection of what is happening on the ground as we can achieve. And so with that, I thank you for listening and your attention. I look forward to discussing this further in the panel.